Well, thanks. This is my first time in Phoenix. I told some people that I feel like it's kind of familiar for all the times I watch sports and I see this beautiful view of this campus and this mountainy thing, whatever that's there. It's really wonderful. Yeah, it's really anyways neat. So thanks for inviting me down here. Um, yeah, I'm going to tell you a story today, and it has the purpose of this story told in the way that I'm going to tell you is not just the specifics of the result, but in some sense the arc of how people do science in kind of precision physics over more than 100 years. In fact, the story will have more than 100 years worth of little sub stories in it at the beginning. And the reason that probably we get invited to give talks and so on this is because this particular story really got a lot of headlines at one point. In fact, in April of 2021, when we released the first results of this experiment, it was in the front page of newspapers all over the world. It was a particularly exciting time for us because if I don't say it later, everything we do in my field, we do blind. So we work on something for 10 years, completely blinded from the result until the very last moment. So we also don't know the result until very short before we announce it to the world. It's all done with precision clocks that are run at frequencies that we don't know, and they're in secret envelopes, and it's its own fun story. But the thing that made this more important to me than these headlines was the fact that it also appeared in one of these PhD comics. If you've ever seen these, at the end of this slides, if you've never seen it, it probably explains the story better than any of us at the collaboration can. It's really great. This guy, Jorg Cham, they're really fun. He explains what happened. So the buzz about this, the reason it was exciting was, is that a little picture of me blocking? Okay. It was really about a simplified version of this plot that I'm showing right here. And in this plot, you can see that over here, there's something called the standard model. And that basically, let's see, click, is the compilation of the work of about 160 theorists around the world over many, many years to determine the quantity that we were testing. And on the right side of this plot are two experimental numbers. What had been done in an experiment I was involved in at Brookhaven National Lab that published its last number in 2004, and this very first tidbit of a result that came out of the brand new experiment, which I'll describe today. So this is just the toe under the tent version, but you can see that it clearly confirmed the Brookhaven result, which at that time could have been something anomalous in the experiment, the only one done like that. And together they make the purple band, and between the two, you have 4 standard deviations, and people thought that was really, really looking interesting, with even at the beginning. Now, since that time, that really represented, I'll try to do it here with this works. Not really this, oh yeah, here, this guy works. So basically, this is a plot of over the 6 years of running, and this is a plot essentially of the amount of data that we took. And the only thing I showed you so far is this, which I don't even remember if it's in the final average of the final thing, because it was pretty ugly data, turned out. So then we got quite a bit more. We got about 30 times, 21 or 22 times as much data as we had at Brookhaven. So that was sort of the goal. And this is just a curve of the statistical precision, which you know goes down with the square root of data of this sort, which involves counts and things. It doesn't tell you anything about the systematics, which is equally important in this story. So in any case, I want to go back and tell you what those numbers were. I know I didn't tell you anything about them on purpose so far. So I want to tell you what was measured, how well was it done, what was tested, what's happened since. These 4 questions I'm just going to answer on this slide, and then I'm going to go backwards in time and then build up to this so you know where we're going. So the first is that we measure something called the gyromagnetic ratio of the muon. So we'll call that G with the mu on it, G mu. Second is we really are measuring what's called the anomalous part of the magnetic moment, and we measure that to a precision, that part to a precision of 124 part per billion by the time I'm done, not the measurements I showed you so far. And what it's doing is it's testing the completeness of the standard model of particle physics. So if the standard model is correctly predicted and we match that value well, then it really confirms things in a way and rules out a lot of speculations about new physics that people have modeled. If the other side is true, like the picture I showed you so far, then If it doesn't agree, then this opens up the hint for lot of other tests and things, because the muon's particularly sensitive to a lot of new physics models. Yeah, so right now the answer is it's going to be confusing. So you're going to leave here a little confused, but my job is to have you be as informed as possible as you are confused. And I hope that'll work. So let me do a bit more on the names, especially for people who haven't seen this story before. So we determined G mu to be this number here that starts with the 2. It has a lot of digits to it. Okay, that's the gyromagnetic ratio of the muon right now. And so this little piece here that I've carved out that's over to the right, that's obviously, if you look at it, it's clear. Now that's G minus 2. So you subtract 2, you get those digits. That's the thing we measure. So the experiment is designed to measure that thing, not the 2 thing. We figure the 2 is there. And then we call that part the anomaly, and that's so A mu is equal to the G minus 2 over 2. So if you take that digits over there, divide it by 2, then you get the thing that we published called A mu, the anomalous magnetic moment of the muon, which is that number there. So you'll hear me say muon anomaly or G minus 2. I just ubiquitously mean whatever this thing is. So the muon is really interesting, and there's a lot of other important moments in the past that I want to take a few minutes to tell you, and some of them might be very surprising for you to learn about. The first is the idea of, just since I had the word magnetic or magnet in this experiment already, let's talk about something that everybody in the room knows about, which is magnetic fields or so. And we go back and you say, all right, a magnetic field is produced whenever an electric charge is in motion. We may have learned a version of that, and we teach that in the classes and so on. You may have made a little thing like that for elementary school to make a magnet out of a nail or so, and professionally you can see some other things. This whole story of magnetism was really completely well known already at the turn of the century in the 1900s. Maxwell's equations and all of this, that was all good. That stuff was solid. And when we teach physics and we learn physics, we don't have any idea exactly what decade it was. We start right there with the book, and it says this is true and this is true and so on, typically goes. But so at that time, this was true. But what we didn't know at the time was some more microscopic part of this. So, for example, when we always plunk down a bar magnet, when we typically do that, and then we might do something like sprinkle little iron filings around it, and you've maybe projected some of that or seen that kind of a thing. The question arises called, well, what causes that? And that was a very important little physics question of the day. And Ampere, Ampere for Ampere's law, Ampere's idea was basically this had to be circular currents, right? This had to be what causes a magnetic field. It looks like it's going to be that. Okay, so in 1908, Richardson suggested a method to test this thing, to test the idea of electron currents in materials that would cause magnetism. There's a little clip of the paper right there. And so he first explained this well-known relationship. So you see the little animation there that an electron spinning around in a current loop like that would have a magnetic moment, basically in the number of turns, the current to the area, which is the EVR over 2. And you could work that out if you don't trust me. And then if you think about the angular momentum, the R cross P, then you're going to get MV and R cross MV. So you get MVR in that one for the magnitude of the angular momentum in that. And if you do the ratio of those two, which is M over L, you just get this very simple thing. You get the electron charge over twice the mass. And so this was known as a recipe like that. And so from that, you could just rearrange this one time and say, okay, the moment there is that M is equal to E over 2M times L, and then you stuck a little G in front of it as a factor that you don't know. And what's that factor? Well, the factor has to be 1 for this to be true. So it's as simple as that. G is equal to 1. This means that basically in an experiment like that, a circular electron would make this ratio, okay? That was what was believed to be inside the magnet. So along comes people that wanted to pursue this, and Richardson couldn't quite get this right. It was hard to do. And the story that really struck me was when I tumbled into a book that taught me a lot about the following story, which is that Einstein himself took some years of his life in around 1915. In the middle, he was doing other little things that most of us have heard of, and none of us have heard of this. But he literally spent time doing experiment will not unlike your experiments that you did. You're going to love this because you could probably have your group set this experiment up in the lab. And essentially, he and DeHaas, who was his assistant, did a very elaborate experiment. When you study this, it's a non-trivial thing, but here's the basic idea. If you hang an iron sample onto a long fiber, you know, these little fibers with a little twist and so on, and basically surround this thing with a circular current, you know, that's a solenoid like this, and then you flip on the field, you'll get a tiny rotation so that you conserve angular momentum. So I do it the following way. Here's what happens. If I, and okay, then he said, Richardson said, assuming that the magnetism of iron is due solely to the motion of negative electrons in the torsional reaction, should easily give a measurable effect. In other words, if you align the spins of those then you're going to get this other thing to conserve angular momentum. And this story is in this book by Peter Gallison. And by the time I've told this a few times, people are buying this on eBay all the time. I've had 2 copies of this book I've worn out by now. I'll tell you the rest of the story on that later. So here's the experiment. Okay, throw the current switch, click. Here comes the current, goes around, makes a magnetic field. And the thing at the top is some little mirror, and the mirror bends ever so slightly. Now, they didn't have lasers then to check this, but they had stuff. And they had thought about external magnetic fields from the Earth, and they had thought about the air currents, and they had done a lot of stuff on this thing. It was by no means trivial if you look at their long list of systematic errors that they studied. And what did they get? Well, Einstein knew it had to be 1. I mean, and he's a pretty heavy guy. So he's a pretty, you know, when Einstein says it's 1, he believed in it. This is called molecular currents. And so he got 1. So actually, they measured G equals 1, and he published G is equal to 1 with an uncertainty of 10%. I know, I love the look on your face. It's true. It's true. And most people don't know this is true. And so, you know, he was very proud, and then other people were proud. But then over the next 10 years, a number of other groups were trying to repeat this experiment. Lots of people getting different numbers and so on. Eventually, some people started to get numbers closer to 2, 1.9, 2.3, things like it started to begin to settle into. And then you read the discussion, the historical discussion of the frustration of this thing. Oh, it couldn't be that, you know, Einstein, it couldn't be. Maybe there's a positive current going in the other direction, for example. That was a conjecture of this. Maybe there's experimental errors. What do we have it wrong, and so on. You know, and so it took a while. The point of this is it took a while before we had quantum mechanics with the Dirac equation, and at which point the solution in the Dirac equation suggests exactly that G had to be 2. It falls out of this thing in a complicated way. It's a purely quantum concept. It's not a spinning charge. It's an intrinsic spin, which gives a magnetism of 1. Like that, and 1/2. So G is equal to 2 comes from, as I said, the symmetry between space-time required by relativity. It's a little bit of a complicated thing, but it's true for spin 1/2 point-like particles like the muon as well. So we start off with that feature. G is equal to 2. Now, let's fast forward with not so much time spent on this history, but these history moments are just as important, and they're actually laid out also beautifully in various books. The next of which is the discovery of the muon itself. So people were starting to build detectors in the early 20s and 30s and so on that had cloud chambers and things like that, and they were seeing tracks and so on, and they knew about cosmic rays. And Millikan, to his death, amazingly, believed that this stuff coming down was gamma rays. We were gamma rays. He was convinced it was gamma rays, gamma rays, gamma rays. And evidence over 10 to 15 years of what these things were punching through was confusing the physics community enormously. We didn't have completely quantum electrodynamics yet, but they had beginnings of this thing. It seemed they knew an electron should make a shower and make tracks and not be so penetrating. And they didn't know what this thing was. And as they kept doing experiments, this muon coming down that would hit this detector, and then a block of iron, and then another detector below it, and they figured out how to make a coincidence circuit, and that blew their minds. Until they started to realize and become brave enough to understand this looks like a new particle that was unexpected. It's the first particle that's discovered that's not part of the basic building blocks of matter, you know, protons, neutrons, and electrons. In 1947, back to some atomic physics experiments, Kush was working with the measurement of the G factor of the electron. And instead of just getting 2, as you get more and more precisely, he gets 2.002. He starts getting a little bit of a deviation. That's credible statistically. And it says, again, the comments are great in these days because we don't write like this. Aesthetic objections could be raised against such a view. It's kind of cute. A decade later, the absolutely revolutionary suggestion by Yang and Wu was this, Yang and Li was this idea that maybe space is not symmetric in the weak interaction. Maybe there's a violation. It was in a solution to a very interesting particle puzzle I'll skip for now. And then, of course, Madame Wu and the other people at Columbia shortly afterwards discovered that was the case. And I have another slide on this to show you. So I'm going to skip that part. It's just very important. And I don't know how many people, but it was great to hear a little bit today about the muonium, where we were talking about muonium with someone. But Vernon Hughes in 1960 discovered this atomic system called muonium. It's a mu plus and an electron orbiting. It's the most perfect little atom to do atomic physics with because there's no structure. 2 point-like particles, one heavy like a proton, one not. And that comes in later because it's those experiments which give you the ratio of the muon mass to the electron mass, which is actually needed in my final step to give you the magnetic moment from the measurements that I make. So let's focus on this radical thought by Yang and Li, which was the Nobel Prize winning thing. And the idea is this question of parity conservation. And in this beautiful paper, and if students are here and have not read this paper, please make sure, put a few of these papers on your bucket list to read. They're so much easier to read than anything modern because modern stuff is very long, full of garbage about electronics and stuff like that. And these papers are just short papers with some physics in it. In some of my classes, we study these papers just for the beauty of it all and the importance of it. But in that paper, he laid out this idea. And shortly afterwards, the Wu experiment, with cobalt-60, but the one relevant to me is the complementary one by Garwin, Letterman, and Weinrich, where they had an experiment at the Nevis laboratory, which they had pions and muons. And having seen this kind of paper, and the early results from Madame Wu, they reconfigured over the weekend their experiment in order to bring muons to rest. And then what you see in this plot right here is they're counting a little spectrometer for the decay electrons from those muons as a function of them changing the magnetic field where the muons live. The muons come in, they're polarized. I'll tell you why later. It actually says it here. So the conjecture was the following. If parity was violated, then as a pion decays to a muon in a neutrino, and they know the neutrino is helicity, then the muons would be 100% polarized back to back because the pion is spin 0. These two things have to be like that. And then if the muon is there, parity violation would make the distribution of those electrons coming out be dependent on the spin direction of the muon. So it becomes its own polarimeter. So there are two beautiful things here. One is that you got the polarized muons in the first place. Secondly, they told you which way they were on average spinning. And that gave you this plot, this beautiful plot that they made. Now, I was able to reproduce this plot at the University of Illinois with undergraduates because in our lab, I did the modern physics lab, and we built this apparatus, and it's still there, I think. I've been gone for 15 years, but it was a fantastically fun thing. So these are big sheets of scintillator here, about this big phototubes, and this is in between them is copper about ½ an inch thick, lots of copper plates to stop it. Muons coming down from cosmic rays, believe it or not, there's mu plus and mu minus, but the mu plus, they're polarized, slightly polarized. And if you stop them in the copper plate right here, they will retain their spin. And if you build a box magnet around there of about 50 Gauss, it's not hard to do, then you will basically able to spin them around and do this. And this is literally data from the students over the course of one semester where we tear this entire experiment apart and build it up bit by bit over the week as students rotate through the lab until you finally can get this thing. Now, if I had only done that, before I was born, would have been nice. So the key to these measurements is that the muon is just a tiny magnet itself. It's a tiny magnet with a pointing thing like that. And a tiny magnet like that means that it could basically put it inside another magnetic field, and it could precess and wobble. It's not straight up and down. So it can, we call it wobble sometimes, but precession is a better word. And in fact, so why was So that's true, but why was it not just G is equal to 2 on this wobble thing? What's the difference there? And the difference is because the muon's magnetism gets affected not by the virtual particles, by the quantum fluctuations with the virtual particles that are out there in the vacuum, which tend to speed it up. And we like to use this animation because this is the view from the muon's point of view. It's seeing these fluctuations of the particles in the standard model, all of them. All of the hadrons, all of the things that are out there. It's sensitive to that, and that speeds it up. And the quantitative explanation takes quantum field theory for this. And so let me take a short detour into this, but in a certain gentle kind of a way. I was trying to think about how to explain that picture for a while, because I had to do it for a general audience at the University of Washington a couple of years ago. And I was looking at that picture and remembering, we're so used to seeing these things we call Feynman diagrams. And I thought, it's kind of a hieroglyphics thing. I looked up hieroglyphics. I think I'm kind of right. It's kind of to people trained in the art, I could give you that picture and a whole bunch of you could go back and start calculating. And where that connection goes from that picture to you doing the calculation is kind of an interesting thing that you have learned by taking the courses in field theory. So where did it come from? What is the picture? First of all, the picture is the following. The white line this is a muon living a life, okay? And the virtual photon is shown here, exchange of a virtual photon. And this little yellow thing is the magnetic field that it's in. This is kind of the picture we've got. And so this was the first step of Julian Schwinger to calculate that number. And that number that is very simple in the expansion of the fine structure constant alpha, the electromagnetic fine structure constant alpha over pi. And then if you do the calculation, you get 1/2. So this is the one calculation I probably was able to do once when I was in graduate school. No chance now, I think, but there was a day. And so it's a very important thing because Schwinger put it on his gravestone here. So he liked it himself. And imagine having a gravestone with an equation on it, but okay. And so then these things get called Feynman diagrams. And of course, the Nobel Prize was won by this trio that developed QED. But by now, this kind of diagram, which gets way and way more complicated, these little things are the same kind of things, but more and more and more loops and things, has 13,000 plus diagrams that have been calculated in quantum electrodynamics. It's by far the most precise theory we have in physics. So where do we get into it for looking for stuff? Because if you really wanted to just do that for QED, then you do the G factor of the electron. People have done the G factor of the electron. Well, way better than us, 1,000 times better. But Feynman diagrams can also be made for heavier particles. So these heavier particles that could be exchanged, for example, anytime you have a photon, you could put a Z in there. It's the electroweak theory after all. So you could put this exchange of a Z or this kind of thing with the W's. Now they don't contribute much, but you can at least calculate these. They're important to calculate. But more importantly is that this blob could be made. And so if this was E plus, E minus, and you were doing a QED diagram, you would call this a vacuum polarization diagram. That's the phrase, vacuum polarization, in the middle of that bubble there. But if you didn't have E plus, E minus, if you had pi plus, pi minus in there, then it's called hadronic vacuum polarization because of the hadronic nature. This is now QCD. This is non-perturbative stuff. This becomes a complete mess, and no one can now write this one down in the room, what it is. And so you can also say, well, what about everything else? How about the kitchen sink? How about some new particle? How about the new theory that you just had? In principle, if it couples to the muon and it has a mass and a coupling, it also will be one of the diagrams that has to be considered in figuring out the precession rate of the standard model. And so that's why our logo in the experiment has this little blob right there. So I'm going to flash this one because this is, when it all comes down to it, this is the problem in the experiment and the theory, this one here. The rest of it's okay. So let's take another look at that diagram. So I draw the diagram one more time. And first I tell you about what's called the data-driven way to do this. And so I'm going to use that phrase data-driven way because it's not calculated by someone. It's this particular method is from data. And it goes like this. So suppose you had that diagram and the uncertainties are all experimental. So suppose you took out a pair of scissors and came down and you snipped the diagram right in half like that. And then you put a little piece of that diagram that I snipped right over here, the photon with pi plus, pi minus part of it. That's part of this diagram now. And now how do I want to generate that? Well, let me use a clean thing to generate that, which is the annihilation of a positron and an electron, which you can calculate accurately. So this version of the diagram actually can be, it comes up with what's called a dispersion relation, will connect that cross sections of this processes to the anomalous magnetic moment part of vacuum polarization in leading order. It's just an integral over a kinematic range of this thing. This is just a kinematic factor, and R is just the ratio of E plus E minus to hadrons divided by a normalization to muons. And people do those experiments, and they do them for decades. And so the data is so amazing. These are all the different channels, not just pi plus. All these different colors are different channels. And these are all energy scales along here where the energy integral will be. And you literally just have to integrate this thing to get the answer. It's just data. And so if you just take the experiments that did the data and now flash forward to 2020 when that green bar was presented as the theorist's idea of this, that was based entirely on this data. You get all these different experiments that contributed to that, and then the gray thing is the average, which was on the second slide there, the green bar before. This is called the theory initiative of the 160 people who are part of this thing in 2020. And this is where the experiment is now, so I've cheated and I've actually told you where we are now. And if you look at the two of those things, it's really sad, and this is why I'm going to leave and run out the door right now, because it would be 5.8 standard deviations, and I'd be going to a bigger celebration. Or one of the people going, maybe. So let's talk about how this experiment was done, if I've got you interested in that. It is such a beautiful idea, and it goes back many generations. The origin of this thing, this is like the 5th generation kind of experiment like this, so it's just an improved version of the recipe. So essentially, the experiment is just going to determine the difference between the spin precession frequency of the muon and its cyclotron frequency. So those are defined by this little old cartoon I made decades and decades ago. If a muon comes in and goes around in a circle in a magnetic field that's into the page, its momentum vector is like black. It's always tangent to that circle. And its spin vector goes a little bit faster. It advances a little bit faster, and that's the anomalous precession frequency. Okay, so if I look at the anomalous precession frequency minus the cyclotron frequency, like the difference between the frequency of the difference between the red one and the black one, then I get what's called the anomalous, then I get the anomalous precession frequency. That's the spin frequency. And that's just equal to these two things, which means that if you can measure this difference, this frequency, and you measure the magnetic field, then you do long division and you get the answer. Simple. So you measure two frequencies and you get the answer. Okay, like that. And just to give you an idea of scale, it takes a muon about 150 nanoseconds to go around here, and every 30 times, 29 times really, the spin laps it. If you think about it as runners in a race, it takes like 29 times around, and the muon goes one extra time. The spin goes one extra time. So this sequence of G-2 experiments, when they recognized that this thing, notice again, I'm measuring the G-2 here. I'm not measuring G. What I did in the Illinois experiment was measure G. That's the number 2 that comes out. But you already give yourself a factor of 850 in precision by doing the difference only here. So basically, the first CERN experiment, had, I don't know, that's a big number, barely got a wiggle. Then they decided to put it in a storage ring like this, and it was very horrible how they got it in there. That's a separate story I could tell you if you ask. And so they got better, 265,000 part per billion. Remember, we're going to end up at 100. And then there was a miracle in the CERN experiment in the mid-70s. And the CERN experiment in the mid-70s recognized something important. But to tell you about why, if you put the particles in a magnet, think about it, they go around in a perfect circle if they go in straight, right? If they have a slight up or down, which any particle would from any beam, then it's going to take 2 spirals until it hits the ceiling up or down. So you have to do something to have vertical containment, but I told you you needed a really good B field, so you can't have magnetic containment. So people put in electric quadrupoles. So what's represented here is like positive plates here, negative plates here, to make a quadrupole electric field, a penning trap, if you want to think about it. And so if the positive particle goes up, it gets pushed down. If it goes down, it gets pushed up. and that gives you vertical containment. Now, if you're a particle, if you're a relativistic particle and you pass through an electric field, it looks like a magnetic field. It looks like it's a motional magnetic field in the equations of Maxwell. So that has to be a new term that affects the precession frequency. This was the trivial terms, and you add this term, which is beta. Beta is the cross E. So it's a cross product between the electric field and the direction you're going in that thing. Here's the trick. Notice that this sits in front of this kinematic factor here. Gamma is basically the relativistic gamma. And what they figured out at CERN was if you tune the momentum of the muons to 3.094 GeV over C, then that corresponds to a gamma of 29.4 or something. It makes this equation go to 0, and there's no effect. You happen to be just living at a beautiful place where the spin precession cancels out of going faster or slower from being off the momentum. So that's the miracle. So in the early 80s, Vernon Hughes organized a workshop consisting mostly of the people from that CERN experiment, the old timers of that old experiment here. In particular, I'd like to point out Francis Farley, who, if there was ever a Nobel Prize for G-2, it would go to Francis Farley. Unfortunately, at 100, he died, but he still was the guy. And he organized this workshop, and the idea there that was new again was, what if you could actually put the muons in directly with a kick, which had never happened before? The way the muons got in there, it was so ugly, you don't even want to know. But a quick story is, first they just brought protons in, smashed them, and hope a muon would, at the end of the collisions, end up on orbit. Then they brought in pion beams, and 25 out of 1,000,000 of those pions would end up on orbit. We repeated that. We actually repeated it. Vernon actually, to be honest, Vernon Hughes liked that idea, and the rest of the collaboration wanted to do direct. And this thing with direct muons, if you could directly put a muon in, it doesn't go around and stay on orbit. You have to push it onto the orbit. So you need to develop something called a kicker, which was what Frank Keenan did in here. And so with that, we ended up with 540 part per billion. And then at that time, by that time, theory was wandering around by the time we finished this thing over the last decade. And so we sort of ended up about here, which is sort of where I was telling you nearly at the beginning of this colloquium, kind of where things were. But along the way, sitting there at the time we were completely done with Brookhaven. It looked like about a 2.8 to 3 standard deviation effect. And I just kept thinking, along with a couple other people, there's no way we can leave this like this in the physics community. We've got to figure out how to go further. It'd just be terrible. It's purgatory for physics. So the thing about that at the time, though, was we were all giving these exciting talks about all the new physics that we would see. There were so many exciting things. The LHC hadn't started yet, and G-2 was pointing towards supersymmetry and stuff like that. One by one, as the LHC was showing, nothing like this in terms of new physics, we were living literally out here in this desert of no one else seeing anything. It was making me extremely nervous. So I have tons and tons of slides that are irrelevant, not in this talk, about all the cool things that we could have seen if things worked out nicely. But okay, so we started to, in about, I don't know, I think it was 2009 already when we started gathering people together. And this was a nice picture in front of the Seattle fountain that I'm sure those of you who've been to the INT and so on recognize, of the collaboration. And the thing I like about this is just to give you sort of some numbers. About 200 people, 35 institutions around the world, about $100 million in the end of the day, about 10 years, and all for one number. And the thing about it is that people in participating come from these different sort of traditional funding and communities. Particle, nuclear, atomic, optical, accelerator, and theorists were literally in this thing to build this thing. So there was no one person who had the knowledge to really build this whole experiment without the expertise of others. And it became a complete teamwork thing. Everyone had to do everything to the precision ultimately possible, or you get the wrong result. The first thing that was obvious was the superconducting storage ring at Brookhaven was designed by Gordon Danby. He's won a big prize for that. He's a fantastic magnet builder. And that had to be used again. There was nothing wrong. The magnet was the magnet. And if you could use it again, and if you could shim it a little better, like a few times better, it would serve our purposes. So, and also you could never rebuild it, and it was expensive. So we basically moved that thing. I don't know if you've seen these pictures before in 2013, but basically had to get the same company that moves spaceships around, shuttles and so on, developed this, brought it around this thing past the arches in St. Louis, eventually with 30 police cars escorting us up the highway. We did this in 3 nights. We paid the tolls. We just went through and brought it to Fermilab to a great party. That was great. And then you had to say, that's fine, but that was just the superconducting coils. And then you had to put this thing back and turn it into a magnet again. All the other stuff came by trucks. So over the next year, this magnet got built, and it was a remarkable thing that Gordon had done because he had built into it a lot of shimming knobs that you could get this field. You want this field as uniform as possible. And we got it to a certain point, using the techniques, this is some of our team doing things, we got it to a certain point, and then we couldn't get it any better than we had it at Brookhaven. And Dave Kawal from Massachusetts kind of came up with this invention. I think it was Dave, but in any case, we ended up at SEMPA at our laboratory taking our laser cutter and cutting 8,000 tiny, tiny little strips of iron, little tiny foils. We had a team of undergraduates at Fermilab basically build histograms out of cups, and they would weigh each one because they were not precise and toss them into the right ones so that we had a distribution of sizes of elements. And we put them in little custom plates. We had mapped this field so carefully with trolleys that we could kind of capture the deviations in the field at the microscopic level by pasting on little pieces of these iron foils above and below all the way around the surge ring. And that was a picture of Eric Swanson, by the way, Will, that he loved doing this. So the magnetic field is measured using pulsed NMR. So proton NMR is the ticket here. And let me just remind you that in a precession experiment for a protons precession, you tip the field over and then it arcs back. And if you have a very, very uniform field, then the free induction decay looks something like this, nice and smooth. But if you have a non-uniform field over the course of something like a cubic centimeter or less, which is the size of the probe, then it will have this funny shapes like that. And to measure this and do all that mapping, we have a trolley here, and the trolley had 17, this trolley had 17, and 2 trolleys, one had 17, this one is 25 NMR probes. And basically we drive it around the ring, and this animation should work. So as we drive this thing around the ring, we are measuring the field everywhere we go, and then putting that into our computer model so we learned how to adjust those shims and things like that to smooth this thing out. And what you're seeing here is the average dipole magnetic field as a function of this thing driving all the way around. And I think what we'll see at the end here, this animation, I have more of these, is basically in the end, the uniformity of the magnetic field at averaged over the entire volume, basically less than 50 part per billion understood. So that was an uncertainty that was really, we more than achieved what we wanted to do with that. Now you have to get the next revolution here beside that was not, it was, look, we got the muons at Brookhaven, but I cannot tell you how ugly it was. For every muon that came in, a hadron came in, a pion came in, exploded neutrons. The detectors were lit up, going crazy with the background, and we still made the measurement. To get rid of that, using the Fermilab accelerators, we basically end up with zero pions, and I'll show you why. You start with HEV muons. They go around this racetrack here that's pretty big on the Fermi campus. That thing gets divided into 4 bunches, each with some ugly shape like this, but at least they work. And then each one of those bunches, one by one, came and hit what was called the old antiproton target. And a long time ago, when there was a proton-antiproton collider at Fermilab, this was a target house right here, and now we strike that thing. And from there, with the HEV protons, we collect 3 GeV pions. The 3 GeV pions go almost 300 meters here, which they're decaying along the way into muons. Then we go around what was called the antiproton accumulator 4 times. It's a very interesting thing. At that point, the protons have fallen well behind, and then we kick it out of there, and only muons go into the storage ring. We're now more than 2,000 meters away from the production of the pion. There's less than 10 to the minus 5 pions left, and essentially no background in this thing. And about 1,000 magnets that have to be running perfectly to make this operate. This is a huge thing to bring it in, and much more often than Brookhaven per second, much more off intensity and so on. And so the ring, there's a nice picture of the ring here. And as you come in the ring, you go through the back door. There's a cutout hole in the back in which there's a superconducting inflector magnet, which allows you to go through a field-free region, come into here, you get a kick here. This is a quick magnetic kick that's pulsed to push the thing onto the orbit. This was the penning trap I showed you about that's located here and here. And these detectors all the way around here are the ones that I built that we'll see in a few minutes collect the decays. The NMR probes are also all the way around here, above and below the whole storage region. Yeah. So one of the innovative things was the development of a tracker system that was in the vacuum in 2 places. And since there's a nice magnetic field there that you know very, very well, an electron, I'll say the word electron, but it's a positron all the time. So forgive me, I'm just going to use electron. So the electrons will, the muon will decay, the electron will curl to the inside, get measured in a track like this, and from that you can actually trace it back and say, where were you born, in a way? Where did you come from by the arc back and where it's tangent? And so we were able to make these dynamic pictures within that storage region of where things were. And you can see the motions. Don't concentrate on the blob, concentrate on the fact that stuff is breathing like crazy, because they're betatron oscillations. So you get into the accelerator physics of this and things are swimming up and down and left and right. It's an enormous number of frequencies are going on in there. To measure that frequency that we needed in the little equation I gave you, the omega A, you basically have these detectors that we built called electromagnetic calorimeters. They're made out of Cherenkov crystals, lead fluoride crystals here. Very, very fast. They look like this. They're rather beautiful. Read out by silicon photomultipliers. There's some looks of the whole thing there that we built all at our lab. And so what you get is if a muon decays into the electron, it may have typically 2.5 GeV or something like that as an energy, just to give you a scale. And that would go into this detector, light it up. It's not a scintillator. It's just flash of Cherenkov light. And that's very fast. What's shown here is just a few nanoseconds, 2 or 3 or 4 nanoseconds. And so with that, if it's above a certain threshold, then it looks like the spin is in the forward direction. And if it's a low energy one, the spin is back. So this animation is important. You're looking at the momentum vector in red, and the one that's going around is the spin of the muon going around. And so what you're seeing here are these curves that are oscillating is the energy spectrum that the detectors see. So we've now converted rotation to energy in this energy. So with that, if I start taking data and I take the events that are above this energy, within seconds, I'm literally building this up in real time. This is a real-time plot you could build up in a few seconds. It comes in so fast. Now, when you're finally done, you add a lot of this stuff together and you get a plot like this with billions of events in it, many billions of events, and you think you should fit that data, and you can fit that data easily. I always call it, well, a professor level fit of this thing has just 5 parameters. The one you would think of right now, you would think, okay, there's an exponential, there's the e to minus t over tau, there's some amplitude to that, there's a 1 plus to that, there's a phase, and there's a frequency, nothing more. But if you fit that, and then you take the Fourier transform or the residuals of that, after you fit that, you no longer see G minus 2. That's where the dotted line would be. That's the main frequency you can all see with your eyes. But what you see is everything else in light blue here. These are all those motions from that thing I showed you before. Things are flying around. These are betatron oscillations that appear as acceptance problems in the detector. But pretty soon you make a more complicated fit like this, has maybe 30, 40 parameters, because you can identify those frequencies. Those are known frequencies with known envelopes. So, you know, what the grad students and postdocs typically did, and there would typically be 5, 6, 7 different versions of this, would be make versions of these functions until the chi-squared was 1, and basically back to this. You see, actually, this is the residuals after the fit. Once you put the terms, it's just dead flat. So the requirement of trusting this data is you have to have a chi-squared of 1, you have to have no residuals, you have to things like that, and multiple people have to have done it independently. Yeah. Okay, so in the end of the day, you still have to get back to what is a mu, and this is our master equation, And basically it has an enumerator, stuff related to the frequencies, and in the denominator, the stuff is related to the magnetic field, okay? And you see a lot of little things here. So this is what we just said we measured, the frequency, but you notice there are a series of corrections here. There are corrections for the electric field. You're not always at the magic momentum. There are corrections from going up and down where you're not always orthogonal to the magnetic field. And there are corrections for things here which are more complicated to explain right now. And here, everything's field tracking, the absolute field. And then these red things here are interesting transients. There's a little eddy current when you come in. There's a little oscillation when you go in. These things we had to learn about and fix and deal with bit by bit. So they've all contributed to the systematic error table. So systematic error table looks, lots of words, stuff like this. You get down to a pretty thing. And, it's about 76 part per billion. So it's below the statistics. And this plot is kind of fun to show because this is a table of all the uncertainties in the experiment. So when you want to ask yourself, could you do a better job of the experiment, it's nice to see the pie chart to see. And people in my group, and not my group personally, but in the collaboration, I'm hearing walk around and say the answer is, you can see it's well balanced and we don't know what to do next, we're done. So I thought this was a good challenge. And if you want to have a question later in the period, I can tell you that I'm already writing up what you could do to fix this. I think it's going to work. If you had any reason to want to do it better. We document everything in this collaboration. You might be curious to know that we have a document database, and there's more than 32,000 documents that support this experiment. And you can read for a while. This is the results. I thought I'd save it for one slide. It's pretty impressive, I think. So these are the three measurements, 3 PRLs from our Brookhaven measurement, and these are the 3 PRLs that we just finished, and this is now the world average. You can see it's a stunningly consistent set of measurements done, always blinded, always with different groups, always with different conditions and different systematics. I think it's kind of a cool thing. So what does it mean now? Well, the early days, it was all about this stuff, supersymmetry, leptoquarks, axions, 2 Higgs. And even with a lot of these constraints, you can get, theorists are infinitely clever, and there's still lots of people that can find ways to say that if it were beyond the standard model, there's a way that they knew that all along was going to happen. Or others that think, of course, it would never happen. So the problem with new physics, so we'll go back to the lessons learned. Let's think again about where I started, where we had the Einstein thing, or nobody knew what the muon was, or the parity thing, or any of that stuff, and think about how they had to kind of come to terms with a new idea, right? And so at the picture, if you're going to claim something new like that, where we sat at the beginning, it looked okay, but then right around the time this was coming out, and temporally I cheated a little bit in the sense because a preprint had come out around the same time that I showed you that. And so first, these are the data-driven numbers. I reminded you of that sort of pretty landscape and this little chopped up things for the hadronic vacuum polarization. These are the data-driven things. And then the lattice QCD versions were starting to emerge, so that in 2021, really just contemporaneous, about the time of our new number, there was the first time a pure calculation of QCD on the lattice of the anomalous magnetic moment was sub% level and therefore competitive. Other than that, it was still work in progress stuff. It was a while before it was fully published, but nevertheless, we knew that they were onto something. And so let me show you the history now. This is kind of interesting. This will bring you right up to 3 weeks ago or so in a sequence. So the Brookhaven experiment here, then run 1 of our experiment there, run 2, run 3, 4, 5, 6, the average, and so on, the final results. So that's the experimental numbers, is with the purple band. Then we go back in time and we look at the recommended theory value from 2020, which was based on all of these green numbers, which also look pretty solid, right? That story. And they haven't gone away. It's not like they've gone away. They were there. But then there was two new things happen. You notice there's a green bar that showed up here and the blue one I just had mentioned earlier here. So what's the green one? I'm sitting at home getting ready to give this talk 2 months before I was giving this talk to the university, and this thing lands on everybody's desk. And it's pretty fast to land on your desk electronically these days, which means you get an email right away. And this was me. It was like, oh my God, what happened? So the CMD3 collaboration does this E plus E minus to hadrons at Novosibirsk in a different technique than most of the rest of them. Although they are listed here as CMD2. This was just an upgrade of the detectors. And they got this result, which was stunningly shifted from everyone else. And it was so scrutinized over the last few years that most of us think we've asked every question of this guy who did it. One person did it. He didn't do it blind, okay, but still, it seems pretty honest. Probably more scrutiny than any of these had gone through at the time, to be honest. And so that was that. And then that seemed to be at the same time this, and people are going, oh, something's going on. And then, you know, then what happened is in the last couple of years, and I'm shortening the intermediate story here tremendously that backs up that these numbers with the lattice are not crazy, but very different lattice calculations also started to agree with this BMW calculation. So we end up with this one and this one and this one. Notice that this is even on the other side, which meant if we wait a few more years, maybe they'll all move over here and we could still be in good shape. So what happened that you've heard about this past year, if you were paying attention, is the theory initiative group that used to say this was the number, abandoned all of this for a while and said, okay, how about if this is the number instead? They literally just tossed out the data. And I thought, and I bought into this, okay, whatever. And I was showing some of my colleagues at UW that, and they said, are they out of their mind? Because basically, you know, these, oh yeah, two more things are coming. I hate to say, but these came over the summer. This was a hybrid version where they used the lattice plus some of this stuff. And this was a new number by these guys just when we thought, you know, the witch is dead. And then all of a sudden these guys, completely new set of data, completely new analysis, just agreed with themselves again back here, Babar. So we're now like, uh-oh, again. So I end up with this thing. This is what we have. And I would say, does this look like the right thing that the theorist should say, given all of this? And it sort of seems like it's already a pretty exaggerated uncertainty, pretty too tight. It's somewhere in here, but it's unfortunately, we don't know where in my mind. So my answer to that is you have to, you know, we're in that early stage still, sadly, you have to be patient. We have to wait. There's a lot more data coming in the green. There's a lot more of the green stuff. Some of the experiments have 7 times as much data they never published before that they haven't analyzed because they didn't think they had to. And so it's a huge effort. Meanwhile, it's cranking deeper and deeper into the computational world that's driven by computational cycles for the lattice community. So they're going to definitely be doing better. We have to resolve this. This can't be right and this right when they get more precise. It's not possible unless there's new physics to be learned just in that of who's got it wrong. So I think just a couple of weeks ago, I was in New York and I was standing in Central Park at the 24th mile of the New York Marathon. And these are the 2 guys that won within 300 milliseconds of one another after 26 miles, sadly. So maybe we're kind of at this point in the marathon, in the 24th mile of G-2 at this point. So let me wrap this talk up with saying, what have I actually, let me step back and say, what have I been trying to create in this story, all right? So first, I start off, was GE equal to 1? And the answer is, it was a well-motivated conjecture from Ampere, pursued by many, but no. You know, the experiments revealed the existence of intrinsic spin and magnetic structure. Was the light particle that was seen in cosmic ray, gamma ray, the gamma rays of Millikan, or Yukawa's meson, which was also thought about as a possibility? The answer is no. It was the muon, and its discovery launched breakthroughs in quantum field theory and determination of the Fermi constant of weak interactions. Was space symmetric? No. The beautiful consequences of parity violation are with us with how it reshaped our entire understanding of the weak interaction physics. And then can one probe the completeness of the standard model by measuring something like the spin of a muon in a magnetic field? And the answer is yes, but we must await the updated standard model predictions in the future, what we learn, to see what nature is going to reveal to us about this story. So each no above, you know, opened up a new frontier, and today's yes may yet do the same, but it may teach us instead that the standard model remains incredibly and stubbornly robust. So with that, I'd just like to flash the pictures of the people in my UW group that worked through the years on this experiment, students, postdocs, and faculty who've all had a marvelous experience over this, have developed all these things in magnetic fields and detectors and analysis and Monte Carlos and running installations and so on. And the entire experiment that made it to a big meeting that we had in Elba, in which we were standing here proudly. At the time, we thought we were going to open the box, and only to find that we weren't ready. And this is interesting plots. This series of G-2 things represents sort of the wiggle plots from the first CERN experiment to where we are now. And with that, I want to thank you for your attention.